So our next speaker is Luca Nesterenko, sorry, who will talk about Phyloformer towards fast and accurate phylogeny reconstruction with self-attention networks.
Yeah, thank you for the occasion of being here. So I'm going to talk about the method we've been developing with Luc Blassel, Laurent Jacob, and Bastien Bousseau for inferring phylogenetic trees using deep neural networks. So the problem at hand, which we are probably very familiar with, is that of reconstructing, given a set of homologous sequences, the binary tree topology, typically labeled with branch lengths, describing their evolution from a common ancestor, with the branch lengths representing the average number of substitutions per site that have occurred in a sequence evolving along that branch. So the problem, as already mentioned this morning, is really hard, given the super exponential growth of the possible topologies in the number of leaves. So for instance, for the trees with 10 leaves, we already have more than 1 million possible topologies. This entails the fact that state-of-the-art methods as maximum likelihood and Bayesian inference need to explore a huge tree space, which makes them computationally costly. And for the same reason, existing deep learning approaches which frame the problem as a classification one, not only they predict only the tree topology, but also are limited to small trees as trees with 4 leaves. So, as we've already seen today, the main drawback of maximum likelihood inference is that it can be very costly. And this entails the fact that maximum likelihood implementations typically have to make several simplifying assumptions about the underlying models of evolution, such as independence between sites, independence between branches, etc. And as we have seen before, this makes the simulations under these models unrealistic and not representative of real data. And usually faster the approach, the more unrealistic the assumptions one has to make. On the other hand, there's a different class of methods that works rather by computing evolutionary distances. Indeed, the branch lengths on a phylogenetic tree naturally define a metric on its leaves, where the distance between 2 of its leaves is just given by the cumulative sum of the branch lengths on the path going along the tree from one leaf to the other. And distance-based methods, such as neighbor joining, have the advantage of being fast and the guarantee of recovering the true tree given the correct evolutionary distances in input. And this also holds for the topology as long as the maximum error between the true and the predicted distances is smaller than 1/2 the smallest branch length in the tree. But how do we compute these evolutionary distances? Well, distance estimation is usually performed again in the maximum likelihood framework, but typically considering only 2 sequences at a time, which can partly explain why these leads to a worse reconstruction accuracy with respect to a full-scale maximum likelihood or Bayesian approach. So the idea is to train a neural network to jointly predict all the evolutionary distances between for each pair of sequences in the input alignment, exploiting all the information contained, given also that these distances are not independent, as they have to satisfy constraints as the triangle or the 4 points inequalities. So we've already seen this idea today. To do so, we take a supervised learning paradigm. Given that computing the maximum likelihood estimate according to a complex model of evolution is typically computationally unfeasible, sampling from the distribution probability is typically cheap, which means that we can generate, we can simulate evolution with a given probabilistic models along known trees to obtain as much training data as we want. To then take a supervised learning approach where we have labeled data consisting in multiple sequence alignments along with the true evolutionary distance associated to it. And then we can use as much data as needed to train a neural network. So this fits into the context of simulation-based inference, having the advantages with respect to a more standard ABC approach that no rejection step is needed, which allows to use all the simulated data for training. And this also allows us to avoid the use of possibly insufficient summary statistics because deep neural networks allow us to use automatic feature extraction. Namely, we can input to the model the whole multiple sequence alignment and let it learn the relevant features that it needs for an accurate prediction. So here we have a brief overview of the method. A multiple sequence alignment after an initial embedding is processed through several layers. Firstly, we obtain from the initial representation representations of the pairs of sequences as is from these representations along the rows that we will eventually extract the evolutionary distances. And then this representation is processed through multiple transformer blocks to obtain in the end, after sidewise average, a vector representing the predicted evolutionary distances that then we can use with a standard algorithm as neighbor joining to reconstruct a tree. So one interesting aspect of framing the problem in this way is the similarity with structure prediction. Indeed, here from a multiple sequence alignment, we're interested in computing distances between the sequences, namely between the rows of the alignment. Whereas in the context of structure prediction, a field in which deep learning has known a lot of success recently, we are interested from a multiple sequence alignment in computing the distances between pairs of amino acids, namely between the columns in the input sequence to obtain a contact map from which we can then predict the protein structure. And indeed, we're using a similar architecture to the MSA transformer, which was employed for protein structure prediction, whereas we're using a different training procedure, namely our model is trained end to end and not with a master language pre-training task. More similarly as the AlphaFold's Phyloformer module is trained. So why are we using self-attention? Well, in a nutshell, self-attention allows us to update the representations of a set of vectors to update their values, making them allowing them to share information between each other, allowing us to obtain some context-aware representations. Specifically, in our context, each vector represents an amino acid in an amino acid position in a pair of sequences, and we can update this representation through several steps, looking either at the other at the amino acids in the other sequences at that position, or at the other amino acids in that pair of sequences. And one advantage is that these update can be applied to a set regardless of its cardinal, which implies that our network can be applied to reconstruct trees from alignments no matter the size, namely the number of input sequences or the sequence length. Another advantage is provided by self-attention is that it is naturally invariant. naturally equivariant to permutation, which is a characteristic that is desirable. Notably in machine learning, often we want the output of our predicted function to be invariant to certain transformations of the input. For instance, if we want to recognize the image of a cat, we want the network to be able to do so even if the image is rotated by 90 degrees, say. Similarly, this property allows us to have the guarantee that the reconstructed tree will be the same no matter the permutation of the sequences in the input alignment without having to recur to data augmentation. So let's go ahead to the results. Oh, we cannot really see the axis. Well, firstly, we tested our method on a fairly standard model of sequence evolution, namely LG. Also modeling heterogeneity across sites with a continuous gamma law. And on the x-axis, we see the number of leaves that the method has been tested on. So we trained the network on a fixed size of trees, namely on trees with 50 leaves, but then tested it on different sizes. And on the left, we can see the Kuhner-Felsenstein distance of the reconstructed tree to the true one, which is a metric that takes into account both the topology and the branch lengths. And we can compare different methods. We have FastME, which is a standard distance method, which basically reconstructs a tree inferring the maximum likelihood estimate for each pair of sequences, then using BioNJ, and then optimizing with SPR and NNI moves to minimize the BME score. Then we have our method in red, Phyloformer plus FastME, which infers the distances as seen before, and then it uses the same algorithm as FastME to reconstruct the tree. And then we have FastTree and IQTree, which both are maximum likelihood implementations. And we can see that our method, when taking into account both topologies and branch lengths, manages to reach state-of-the-art performances. And on the in the right panels, we can see these metrics kind of decomposed into two components, namely the mean absolute error on the predicted distances, where we see that given that this is the loss function that we actually optimize, our network performs really well with distance predictions that are state of the art. And we can look at only the topology, where we see that our method is, if we only look at the topology, isn't as good as maximum likelihood methods, but still manages to outperform existing distance-based methods, no matter the number of leads. But as mentioned before, the advantages of such a method is that it can allow us to take into account more complex models of evolution. For instance, phenomena observed in empirical data as coevolution, where pairs of residues evolve together, mostly because of constraints in the 3D structure. If two amino acids are close in the 3D structure of a protein, they typically will evolve jointly. Otherwise, the protein wouldn't be functional anymore. And vice versa, these coevolution patterns are typically also exploited to infer from a multiple sequence alignment 3 contacts in these 3D structures. And this phenomena is typically disregarded by current maximum likelihood methods, as it would make them intractable. But on the other hand, we can simulate coevolving sites using an empirically inferred transition matrix for pairs of residues, which was inferred and published in this paper, Cherry Mel. And In this context, we can see that indeed, using an approach as ours is quite advantageous. Here we have two instances of our method. In red, we have the same model that we've seen before that was trained on the simulations under the LG model. And in purple, we have the same model that has been fine-tuned, that has been further trained with a lesser number of steps on the simulations under the cherry model. And we can see that in this case, the performances are really the best among all the methods, not only in terms of distance, but also in terms of topological accuracy. And this also shows the flexibility of the approach, namely the fact that having an already pre-trained model, we can then fine-tune it on the different models of evolution. And one interesting thing about this result is that even if typically deep neural networks are seen as black boxes, we can still get some insights on the network's inner workings, in the case of transformers, looking at the attention maps, namely looking at the weights that are given to the vector representations of different features to update the representation of the alignment. So here we are visualizing the attention maps corresponding to the updates that are given side by side. So in a nutshell, the lighter are the squares, the more attention is given to a given position along the sequences. So here we are only looking at the first 20 residues of the sequence, and we see that a pattern emerges. Indeed, I didn't mention this, but in the simulations that we carried on, the co-evolving sites are side by side, which doesn't really matter because no positional information is available to the network, and the maximum likelihood and the other methods also are ignorant about the positions of the amino acids inside the sequences. And we can see that indeed the networks, the coevolution pattern emerges in these attention maps, which means that the network learned to capture this coevolution phenomenon in the input data. Whereas if we test the model trained on LG data, we don't see this pattern, but only the pattern along the diagonal, meaning that each amino acid is mostly paying attention to himself. One interesting thing is that the same pattern can actually be observed when we test the LG model, which has never seen coevolution in its life, on these cherry data, which is interesting. The fact that it's still capable to identify co-evolving sites, and which can maybe explain why the non-fine-tuned model is still performing quite well on this data. So for instance, for 10 sequences, it's still the one predicting the best topology, and there is a much wider gap between him and FastME, both in terms of mean absolute error and Kuhner-Feldstein distance, although both the methods are under model misspecification, as FastME is using the LG model for the distance prediction, and this model has been trained on LG data. And in terms of speed, well, this has mentioned before. Of course, there is a choice to be made. Training these networks can be computationally costly, but as I mentioned, once it has been done once on a specific model evolution, this can be done with a smaller cost to fine-tune it on another one. And also this can be done once, and then during inference, the method is actually very fast in terms of performances. So we see here on a log scale, we don't see the axis, but the elapsed time for different methods with hours in red, and then FastME, FastTree, and IQ3 with model finder, which one may want to use in a context where the model at hand isn't actually implemented by IQ3, so one has to choose the best fitting one amongst the ones that are. So some future work will include the introduction of a measure of uncertainty in the predictions of the network, the training on more complex and realistic models of evolution, as this is the context in which the approach is the most practical, and possibly the development of the differentiable tree reconstruction algorithm for end-to-end training without this two-step in distance prediction and then tree reconstruction, and further improve scalability, which will be which will come easier as faster and faster attention implementations are developed, as is the case right now. I wish to thank all my collaborators and you for the attention.